Complex logic circuits. To realize other Boolean functions of multiple input variables, the basic circuit structures and design principles developed for simple NOR and NAND gates in the previous sessions can easily be extended to complex logic gates. The ability to realize complex logic functions using small number of transistors is one of the most attractive features of NMOS and CMOS logic circuits. Consider the following Boolean function as an example: z equal to a into td plus e plus pc bar. The NMOS depletion load complex logic gate that is used to realize this function is shown in figure. Inspection of the circuit topology reveals the simple design principle of the pull-down network. Or operations are performed by parallel connected drivers, and operations are performed by serial connected drivers. Inversion is provided by nature of MOS circuit operation. The design principles stated here are for individual inputs and corresponding driver transistors, and also be extended to circuit subblocks so that Boolean or AND operations can be performed in a nested circuit structure. Here you can see in this figure NMOS complex logic gate realizing the Boolean function given in equation. Thus we obtain a circuit topology which consists of series and parallel connected branches as shown above. In figure, the left NMOS driver branch consisting of 3 driver transistors is used to perform the logic function a into d plus e, while the right hand side branch performs the function bc. By connecting the 2 branches in parallel and by placing the load transistor between the output node and the power supply voltage VDD, we obtain the complex function given in equation. Each input variable is assigned to only one driver. For the analysis of design complex logic gates, we can employ the equivalent inverter approach already used for the simpler NOR and NAND gates. It can be shown for circuit in figure that if all input variables are logic high, the equivalent driver WL ratio of the pull down network consisting of 5 NMOS transistors is W by L equivalent 1 by W by LB plus 1 by W by L C plus 1 by W by L A plus 1 by W by L D plus 1 plus W L by E. For calculating the logic low voltage level VOL, we have to consider various cases since the value of VOL actually depends on the number and the configuration of the conducting NMOS transistors. In each case, all possible configurations are tabulated on the next page. Each configuration is assigned a class number which reflects the total resistance of the current path from Vout node to ground. A minus D class 1, A minus E class 1, B minus C class 1. A minus D minus C class 2, A minus D minus B minus C class 3, A minus E minus B minus C class 3, A minus D minus C minus B minus C class 4, assuming that all driver transistors have the same W by L ratio. A class 1 path such as B minus C has the highest series resistance, followed by class 2, class 3, etc. Consequently, the logic low voltage levels corresponding to each class have the following order, where each subscript numerical represents the class number: VOL1 greater than VOL2 greater than VOL3 greater than VOL4. The design of complex logic gates is based on the same ideas as the design of NOR and NAND gates. We usually start by specifying a number of VOL value. The design objective is to determine the driver and load transistor sizes so that the complex logic gate achieves the specified VOL value even in the worst case. The given VOL value first allows us to find the WL load and the WL driver ratios for an equivalent inverter. Next, we have to identify all worst case class 1 paths in the class 1 circuit and determine the transistor sizes in these worst case paths, such as each class 1 path has the equivalent driver ratio of W by L driver. In this example, the design strategy yields the following ratios for the three worst case paths: W by L A is equal to W by L D is equal to W by L driver. W by L A is equal to W by L E is equal to 2 W by L driver. And W by L B is equal to W by L C is equal to 2 W by L driver. The transistor sizes found above guarantee that for all other input combinations the logic low output voltage level will be less than the specified VOL. Complex CMOS logic gates. The realization of the N-net or pull-down network is based on the same basic design principles examined earlier. The PMOS pull-up network, on the other hand, must be the dual network of N-net. This means that all parallel connections in the NMOS pull-down network will correspond to a series connection in the PMOS pull-up network, and all series connections in the pull-down network correspond to a parallel connections in the pull-up network. Here you can see the figure construction of the dual pull-up graph from the pull-down graph using the dual graph concept. Figure shows the simple construction of the dual P-net pull-up graph from the N-net pull-down graph. Each driver transistor in the pull-down network is represented by an edge, and each node is represented by a vertex in the pull-down graph. Next, a few vertex is created within each confined area in the pull-down graph, and neighboring vertices are connected by edges which cross each edge in the pull-down graph only once. This new graph represents the pull-up network. The resulting CMOS complex logic gate is shown in figure. Thank you.